I guess we can kick things off. So welcome everybody that's here. This is the next installment in the AV over IP Task Forces series that we've been tasked with doing periodically between the last conference at Iowa State and the next one at NC State. And today we're going to be joined by Jonathan Moore from the training team on QSC. Lots of familiar faces that are strong and active members of ETC. So I'm sure you've seen him before or worked with others on his team. Jonathan presented with us at the pre-conference workshop in Iowa. And one of the things that we hadn't planned for that we spent quite a bit of time talking about and was actually really active and engaging was clocking domains, picking clock leaders and what environments they do and don't work in, and what the compatibilities are between different platforms and everything like that. So that's what we wanted to encapsulate in this session. We've got additional sessions coming up. The next one is about SDVoE, which is software-defined video over Ethernet. And then we're working on a session with Audinate to do just a Dante crash course that's all about their flavor of audio. So without further ado, Jonathan, the floor is yours. And thank you so much for being here. This is going to be a really great session.
Great. Happy to be here. I get to talk about this all the time. So it's something very relevant in the space, as well as kind of the industry in general. So everything I'm going to be talking about, we're going to go pretty fast. There is a lot to cover. I'm going to try to give you time to let your brain saturate in the information, but it is going to be a little bit of review and maybe some new information. So try to hold some questions till the end. I'm going to try to get through the bulk of the class so we have time to ask some questions at the end. So I'm happy to do that. And without further ado, let's talk about planning PTP clocking domains with Dante, QLAN, and AES67. So one of the things you might be asking, well, Jonathan, you're from QSys. What does QLAN have to do with this? Well, one of the things that this training session is going to go over is how QLAN is going to relate to Dante and AES67, because a lot of these technologies rely on some of the same mechanisms in the AV over IT or IP world. So there's a lot of technology crossover here. So with that being said, some of what we're going to be talking about does relate to AVB. So other manufacturers do use AVB. AVB uses a different form of what we're going to be talking about. Then I'll mention some of those things as we go. So without talking any more about PTP, let's do some review of networking. So I want to give you some general overview and then some specific ties into what we're going to be talking about. So very basic things. Let's kind of start with the typical messaging that we see on a network infrastructure. So what we're going to be talking about mainly, the communication between the devices that we're going to be discussing. That primary communication is going to take place, or is going to be facilitated with UDP and TCP. So UDP is a type of transmission protocol, as well as TCP. So both of these are transmission protocols. However, they have two different styles of operation. So UDP, user datagram protocol, it is a one-way, hope you get it sort of messaging, kind of like sending a letter in the mail. You hope it gets there, but there's no feedback if it actually does, unless you pay for it, right? But UDP is a one-way messaging protocol. There's no way for us to know if the receiver actually got the message. So one thing that UDP is good for is sending a lot of messages really fast, but it's not necessarily the most reliable transport. So we're going to talk about a little bit about that. One of the most reliable protocols is TCP. TCP uses a mechanism of sending a message and making sure that device sends an acknowledgement back. So TCP sends a message, waits for that reply back, sends another message, and so TCP ends up being it ends up utilizing a lot more overhead on the network. However, it is a very reliable transport method. So again, the protocols that we're going to be talking about today, utilize UDP and TCP as the transmission protocols on the network. Okay, so talking about the network and a basic network switch. Ethernet switches have the ability to resolve an IP address, well, at least layer 2 and layer 3 switches have the ability to resolve an IP address to the MAC address, the hardware address of a device on the network. So we can see in this visual here, we have a transmitting device over here on the left-hand side that is sending a message to another device on the network, and it's only intended to be sent to that one device. And so this would be considered unicast. So anytime that we're going to be sending a message to one device on the network, that is going to be a unicast flow or a unicast transmission. So we can see we're gonna send a message to red, we're going to send a message to green and blue. They don't know anything about each other necessarily, but the switch knows what port that they are plugged into. So when this transmitting device sends that message out, the switch is going to receive a header that says, hey, I'd like you to send a message to this IP address. And the switch says, okay, and sends it to the correct device on the correct port. So at the very basic level, this is an ARP table. So address resolution protocol, that's what that stands for. So it resolves an IP to a MAC address. And this is a big part of how this technology is working at the very basic level. Okay, and then we start to talk about multicast. So one of the things about different between unicast and multicast is that unicast a lot of times is going to use that TCP protocol to get messages out to another device. However, when we talk about multicast, when we create a multicast transmission, we're sending that multicast into this switch, and then saying any devices that want to receive this traffic, they can receive it. So the encoder doesn't know what is connected to it or what may be resolving and connecting to this IP address or this MAC address. We're just sending this out to the world, out to the switch, and the switch is going to send it where it goes. Now, out of the box, multicast will be sent to all of the ports on a basic switch without any management enabled. So it acts a lot like a broadcast, which by default always goes to all ports on a switch. So with no management in place, multicast will go out all of the ports on a switch. So let's talk about how, in general terms, and especially in smaller AV over IP instances, for sure, why IGMP, or Internet Group Management Protocol, is a great way for us to manage that multicast. So if we have one device, or maybe just a small number of devices sending a low amount of traffic via multicast into this switch, we're probably not going to have an issue with traffic. However, if we consider a single gig network switch, there's a limit to how much data we can send across each one of those ports. And so in this graphic, we're actually seeing we have 3 decoders in place, and they're all sending 800 megabits per second into that switch. And so with no management in place, all of these devices are going to be receiving up to 2.3 gigabits per second, which is way beyond what they're designed for, right? And so this scenario happens quite often. And this scenario will result in devices just not working. Okay. So when we want to manage that protocol, typically we're going to use IGMP to do that. And so the switch that's going to run that protocol is going to be a basic level 3 or full level 3 switch. So that means it's going to be managed. It has layer 3 functions available to it. What we do with IGMP is we say, hey, Mr. Switch, I have, that's not what we want. I have a stream that I want to send to the network, but I only want devices that want to subscribe to that. So we can take this example really quick. So our red encoder is sending to the network, but my laptop and my media player have no need for that multicast stream. So the switch using IGMP is going to prune that multicast and not send it out to these devices, but will send it to this decoder who is going to request that stream or subscribe to that stream. Okay. So we're jumping a little bit into this. So there's a lot of nuance here that I'm just kind of skimming over. So again, think of this as a pretty high level view here. So why QoS is going to matter in these instances where we have IGMP, multicast, and clocked audio is we've got to make sure that the network clock and the audio that we're sending, and sometimes video, when we're sending it across the network, we have to make sure that that traffic gets to its destination in the specified time, or the time in a constant cadence, as well as a constant time. So we don't want this to be incredibly variable, and we want this to be as quick as possible. So these communications really matter. So QoS can help us make sure that traffic and packets are delivered on a perfect cadence, maybe not a perfect cadence, but always a relatable cadence, and make sure that if at any point we have an issue on the switch and there's too much traffic going to the network ports, that the devices that are receiving that network clock will continue to receive that based on the priority that we set using QoS. Okay, so something to keep in mind. So when we have employ PTP, and we're going to talk a little bit more about what PTP is here in just a second, but when we employ PTP on a network for clocked audio, we have to make sure that that round trip time for those packets is less than 310 microseconds. If not, we're going to end up having issues, and this is usually where I see customers having problems with clocked audio, whether that be Dante, QLAN, AES67, any of the above. So keep in mind that the physical cabling, the layer 1 cabling within a network, also introduces latency. So a typical cable, Cat6 category cable, that is going to connect a peripheral device to a network switch, is going to introduce up to 12 microseconds of delay just over those electrical pulses that go between those two devices. The switch itself, a typical gig switch, is going to take around 10 microseconds to forward that traffic, and then we got to get that cable to another destination, which can take another 12 microseconds. And then, so if we consider gigabit networking, this could take up to 34 microseconds just to get the packet across the physical infrastructure. Okay. So these things we have to keep in mind, especially when we introduce multiple switches into the equation, as well as when we have a lot of devices in the system. What QoS does is we say, hey, we have all of these packets in this stream of Ethernet frames, and based on a marking that's available in that packet, in that network packet, we're going to assign a priority to that packet. We're going to say it's a high priority, a medium priority, or a low priority. And then we're going to place that on the managed switch. We're going to place that into what's called a queue. And so so we make sure that the high priority, high and medium priority packets, they get processed and sent as fast as possible based on the policy that we've set. And then traffic that is low priority, like control traffic and other things, we're going to send it whenever we can. Whenever there's a chance to send that, we're going to send it without a emphasis on priority. Okay. And so what this looks like when we're actually looking at switch models in the industry, low-end switch models may use a 4-class model, so not super common. So your very low-end switches are going to utilize a queuing system like this. Your typical switch, kind of the medium tier switch, It's going to use what is usually an 8-class model. We're going to have up to 8 queues on that switch. And then your highest level switches, your enterprise level switches, are going to utilize multiple queues, 12 if not more queues. We can send those packets into queues across network infrastructure and make sure that all of those packets with a priority set get to where they're supposed to go in time. So one of the things to keep in mind with QoS, and this is part of my conversation with a lot of IT folks out there, is that when we use priority queues, it's pretty important, especially with PTP, that we maintain the queue number or the strict priority queuing across the entire infrastructure wherever we're sending that clocked audio or wherever we're going to see PTP packets. Okay. So switching gears just a little bit here, we're going to be talking about Dante. So what I'd like to point out is, what are the advantages of Dante versus what we, traditionally would have used for classroom systems or AV systems in general, which would be typically analog systems. And then as we move into this AV over IP world, what are the benefits of that? So with Dante Audio, if we take what used to be, the go-to idea of being microphones, instruments, general analog devices into an analog infrastructure, an analog AV system, we got to use a lot of wires. We got to use a lot of connectors. So in general, if we're looking at some of the typically used analog connectors out there, there are quite a few of them. So what that also introduces is a lot of complexity, and it also can introduce the need for compatibility and the need for adaptability. So again, makes things more complicated when we have these bespoke technologies, these bespoke cablings, these bespoke connectors for that infrastructure. So as we move, especially in the higher education world, beamforming microphones that we place in the ceiling, on the wall, on a table, those allow us to gather the same analog data from what would have been a microphone before, take that same analog, convert it to digital, and then send it across an infrastructure in a very scalable way. So if we take this example of these beamforming microphones and say our wireless microphones and maybe even a Bluetooth wall plate, using a single category cable, I can connect these devices to a network switch, get my audio from the room. I could even connect other devices to an analog mixer that has a Dante card in it, for instance, connect that to a network infrastructure, and then be able to deliver that deliver it in a scalable fashion. But also, if we have to distribute that, it becomes extremely scalable and one of the best ways to perform this operation. So if we are gathering that Dante traffic, we could send that to many locations at once. So if we have one source, but it needs to go to a lot of places, clocked audio or AV over IP is a great way to do that. And then, or if we, taking the same scenario, if we have a lot of inputs that need to go to a lot of different places, the second, let me actually turn on my laser pointer. I was hoping y'all could see that. I forgot to do that. In our unicast look here, where we're sending a lot of inputs to a lot of different outputs, this allows us to create a very scalable, large system over very cheap infrastructure. Okay. Let's talk about Dante Audio itself. So typically when we're talking about Dante Audio, Dante is, as a protocol, has to be packaged in a way that is digestible in a standard format across a lot of different devices. So as a protocol, Audinate created Dante to work as a flow, and inside of that flow, they place a number of bundles. So what this typically looks like is we have a single flow, which would be a stream. So we have a stream or flow, and inside of that stream or flow, we have up to 4 channels. So we have a bundle of channels inside of a single stream. And typically, that's going to be a unicast flow from one device to another Dante device. Dante does support multicast audio, but that's a whole nother conversation that we're not going to cover today. So when we're talking about the number of channels on the network, the number of flows that are required to perform whatever we're looking for here, we have to keep that in mind when we're designing our Dante systems. But one of the great things that flows give us is the ability to is determine exactly how much traffic is going to be created by that Dante traffic. So what that means is Dante and other clocked audio that utilizes streams and bundles in this way are deterministic. We know exactly how much bandwidth they're going to consume. So that makes it easier when we're designing infrastructure. Okay. And then one thing to keep in mind, we're going to talk about PTP a little bit more, but one of the things to keep in mind is that devices that are utilizing one version of PTP might...
Jonathan, since you've turned on your laser pointer, your audio is choppy when the mouse moves for me. I don't know if it's
really
crunching the processing on your computer, but we could actually see your mouse cursor before, and that might have been better.
Okay. All right. Is that I'll move that around.
Yeah.
Is that better?
All clear.
Oh, interesting. Good to know. Good to know. So when we have Dante devices that may be participating in one version of PTP, may not always participate in the other version of PTP. But if it is a device that does support both versions of PTP, there has to be a boundary clock, whether that be somewhere else on the network or internally to that device, to send a clocking pulse between version 1 and version 2. So if that's confusing to you, totally understand. We're going to cover a little bit more about that here in just a second. But just know Dante devices have some of this nuance that we have to think about when we're designing our clocking domains. Okay, with all of that, let's talk about clocking domains. So we got through our network review, so that's going to be relevant to what we're going to be talking about. Let's actually talk about our clocking review. So I've mentioned it a couple times now, and you're probably like, Jonathan, what the heck is PTP? I have no idea what that is. But what PTP is, it is the Precision Time Protocol. So the Precision Time Protocol is a suite of protocols and standards that have been put in place by the IEEE standardization organization. And specifically, they have designated 1588 as the designated marker for PTP in their documentation, right? So IEEE 1588, if you see a mention of that, what we're talking about is PTP. And so with Dante, QLAN, and AES 67, we have a couple of things to consider here. Dante is going to use one flavor of PTP, which is PTP version 1, and that's going to be designated as 1588-2002. So that designates that it is PTP version 1. And then we have other devices on the network, and even other Dante devices that will speak AES 67. So AES 67 devices and QLAN will utilize PTP version 2, which is designated as 1588-2008. So one of the things to keep in mind is our visual over here on the left here. This is what it looks like when we actually generate a clock, a network clock, so a synchronization between devices on the network. This is what that looks like. So we have a synchronization packet that goes out to a peripheral or slave device from the clock leader. We have a synchronization pulse. Then we have a time alignment pulse packet. Why does that keep happening? That goes out let the device know if it's on time or off time. So what can happen here is if we have a clock generator sending out a time, and then a peripheral device that's going to be receiving that time, it's always going to respond to the clock leader that it is clocked with it. One of the things in this mechanism that takes place is the ability for that slave device to request a delay packet. And what that allows that device to do is receive an updated timestamp from the clock leader. And so it matters greatly when we're selecting our clock leader on the network. It matters the quality of that clock leader as well as the capacity of that clock leader. And I'll talk a little bit more about that a little bit later. But the big thing to keep in mind is that PTP is a very precise protocol. As I mentioned before, the time that we're talking about here, as far as these pulses, this time pulse and this response pulse, mentioned it before on our slide switch. That travel of a pulse and a response, that has to occur in less than 310 microseconds. So what that means, and built into that, is a 30 microsecond jitter variance. Jitter being jitter being noise on the network. When we have lots of things talking, jitter can be introduced, especially if we do not have QoS involved. So with that 30 microsecond variance, that gives us the base config of PTP, gives us the base specification of 280 microseconds to get packets from one place to another. And so when we're talking about that, that's a very short amount of time. And so we have to make sure that our network infrastructure is built to handle that. Okay, so PTP requires multicast on the network. It uses an algorithm called the BCMA, or the Best Master Clock algorithm. And this algorithm runs every single time a new device is discovered, especially a new PTP device is discovered on the network. So that BCMA will run every single time, and it will select the best clock based on a set of factors. And it's extremely sensitive to jitter on the network. And one of the things we want to do is make sure that QoS protects those PTP packets on the network. And one of the biggest takeaways and things to keep in mind is that PTP version 1, i.e. Dante, and PTP version 2, which would typically be AES67, those two things are not backwards compatible. So like mentioned before, what that means is there has to be what's called a boundary clock that exists on the network, as well as devices that speak version 1 and version 2. There's an internal boundary that occurs between the software layers of that PTP clock generation and clock following. Okay. Let's talk about some clocking scenarios. Some of these are going to look pretty familiar to you. And one of the things you're going to notice is that we have some QSC or QSys branded boxes here, but all of the concepts that we're going to be talking about apply to the same things, apply to all of the other protocols that we're talking about. So Dante and AES67 are absolutely part of what we're going to be talking about. So I'm going to mention QLAN a couple of times, and just know that that is our streaming protocol for audio as far as QSC goes. And it utilizes PTP version 2. So just keep that in mind as we go through some of these slides. Okay, so we have two pieces of gear on the network, and they have no audio peripherals between them. And in my DSP design, I only have analog audio in and analog audio out. I'm not relying on any clocked audio in the system. So no Dante, QLAN, or AES67. So between these two devices do not need to speak PTP on the network. So they do not need to clock together because we're not sending any audio on the network, either between each other or to other devices on the network. So there is no clock generated when there is no clocked audio designed in our DSP. Okay. Scenario 2, let's talk about peripherals. All right, so again, keep in mind this is PTP version 2. So in this scenario, we have two DSPs, we have two QSys cores, and each one of those cores has a peripheral device that's going to be sending and receiving audio to and from that DSP design. So by default, based on a number of factors, core 1 is going to win this BCMA election. Remember, that's our best master clock algorithm. And what it's going to do, because we do have audio on the network, we're not sending audio between these two DSPs, but we do have audio on the network. So we are generating a clock, and inside in that that clock is going to be utilizing a domain of 0. Well, what's a domain? Well, a domain is a logical grouping of PTP sensitive devices on the network. We're not going to dive too deep into domains, but just know that domain 0 is where you're going to find 99% of the Dante and AES 67 installations out there. Okay. So in this scenario, core number 1 ends up becoming the leader on this PTP network because it just so happens to have the lowest MAC address, between these two devices. So BCMA chose this core as the clocking leader, and until we have another device added or taken away from this network, that's not going to change. Okay. So another scenario. So now what we're going to do is introduce the idea of adding priority to our clocking leader. So what this might look like in those of you who have used Dante, exactly what we're going to be talking about is related to something you see in Dante Controller. Has anyone seen select as preferred leader in Dante Controller? Any hands? Feel free to speak up, or any hands like that. Anyone seen preferred clock leader in Dante Controller? Well, let me tell you, it's there, and it's something that you can use to influence who becomes the clock leader on the network. So let's talk about now. This does apply to QSys cores, but the discussion is critical to what we're talking about. Okay, so this is going to be talking about PTB version 2. And when we start talking about clocking boundaries, this is going to become even more important. Okay, so we have that same scenario where we have two cores and their peripherals, but now we're going to introduce priority. So in the BCMA, here are the things that are considered before a clock leader is selected. So by default, deep down into that protocol, a priority number is assigned to a device on a network. As a PTP sensitive device, it's always going to have a priority number. Okay. These other things, I'll mention them, but they are not relevant to what we're talking about. So a good quality clock leader will have a high class, a high accuracy, and have a very small variance. Okay. Next thing, as far as this class is concerned, the next thing that's considered is priority 2. So priority 2 is the next thing that will be considered if everything else matches between all of the potential clock leaders on a network. So priority 2 is considered, and then finally, if everything else matches, the final deterministic factor is the UID or the MAC address of the device that could potentially be our clock leader on the network. So a lot of times you'll end up, you might be like, why the heck did this microphone, out of all the microphones on my network, why did this microphone end up being my clock leader? Well, there can be a lot of reasons for that. But typically, if you use a Dante device out of the box, all of our priority 1s and priority 2s are exactly the same. So the determining factor ends up being the MAC address. So just know that the MAC address is usually the determining factor when we're choosing that clock leader. So anytime a device has the lowest MAC address, if you were to convert that to a decimal, anytime that's the lowest, the lowest MAC address, that's the one that's going to win. Okay. All right. So in this case, we set a priority for our core number two. And if we run BCMA again, we're going to see that core 2 will actually win the selection because we dropped our priority 1 and priority 2 values in the PTP version 2 space. Okay, but keep in mind that these two cores are still in that domain of 0 in the PTP version 2 space. But with that, let's go ahead and talk about another scenario. Okay, so this is a bit of a feature that's unique to QSys cores. I'm not gonna spend a whole lot of time on this, but this is something that utilizing the standard protocols through PTP, QSys can take advantage of alternate domains in the PTP version 2 space. So what does that mean? That means that what we can do in each DSP design, if we do not want those designs to clock together, even if they have those peripheral devices with them, if we want to separate the network clock between those DSP designs, we can place those designs into alternate domains, alternate PTP version 2 domains, so that if I make a change on the network, or if I push a design, if I make any change on the network, these systems will not clock together, and i.e. will not run the BCMA algorithm every time something changes. Because guess what happens every time that the BCMA runs on the network? So when we're selecting our clock leader on the network, all audio is muted. Okay, has anyone experienced that problem? So when you see you're having some weird network issues or anything like that, has anyone experienced just random muting of the audio on the network? Anyone seen that? Yeah, thank you. I see a couple hands there. So that is a result of our BCMA running over and over and over again. So if you see your clock leader changing all the time, that's indicating that we have an issue on our network infrastructure. Okay. So as an example, I can run core 1 and its peripheral in domain 0, and I can run core 2 and its peripheral in domain 1. So these two devices are the core 1 and core 2 are their respective clock leaders in their PTP domains. Okay, so again, that allows us to separate their network clocks. They're not clocking together. Okay, so now let's talk about QSys cores and well, DSPs with Dante enabled and AES67 devices. Okay, so Dante devices that are any bit modern are going to be using modern chipsets that are capable of transmitting and receiving Dante and transmitting and receiving AES67. Now, remember that Dante audio uses PTP version 1 and AES67 uses PTP version 2. And remember, those two things are not compatible with each other. So we have to have a clocking boundary. We're going to talk about that here in a second. So on Dante devices, through Dante controller, if we want to enable this AES67 mode, which is going to turn on PTP version 2 and AES67, this is going to now make a device that was only utilizing PTP version 1 in domain of 0 to now utilize a clock for version 1 and version 2 on the network. Okay, so again, that's going to introduce our boundary clocks to the network. All right, so what does that look like? You're probably, Jonathan, I'm lost. I don't know what you're talking about. So here is our visual of what we're talking about. Okay, we have our DSP over here on the right, and it has its own peripherals. And we actually have two of those DSPs, and they're all in PTP version 2 domain of 0. Okay. Now what we've done is we've introduced a device on our network that has an older chipset, an Ultimo chipset from Audinate that is only capable of Dante communication. So it's only capable of speaking PTP version 1. It has no concept of what of the PTP version 2 clocking domain on the network. Okay. We've also introduced a Bluetooth wall plate that has the ability to transmit Dante and AES67. So by default, based on out-of-the-box values, this device that is AES67 capable is going to win our clock leader election because its priority values are lower by default than any other device on the network. Okay, so by default, when we enable AES67 on Dante devices, those devices now have a priority of 127 on the network, which is lower than most devices on our clocking network. Okay, so that Bluetooth wall plate becomes our clocking leader and our boundary clock between version 1 and version 2. Okay, so again, this is somewhat unique to QSys cores, but one thing we can do when I was talking about priorities, we can change the priority of the DSP design in order to influence the clock leader that is selected. And how do we do that? Well, going back to those priority values, priority 1 gets lowered below a value of 127, and the priority 2 value gets lowered below 127 as well. So when the BCMA runs, when it's selecting a clock leader between all these devices on the network, it's going to consider which priority it's going to consider priority 1 first. And if anything else matches on that Dante clocking network, or excuse me, on that PTP network, it's going to then look at priority 2, and based on that, it's going to either select the device that has the lowest priority 2, or what's the final one? The MAC address is the thing that is the determining factor if our priority 1 and priority 2 values are the same. Okay, so by default, one more time, Dante devices that have AES67 enabled by default are going to have a priority 1 value of 127. And so by modifying our priority values for core 1, we can influence it to be our clocking leader for our network. Okay, so instead of our Bluetooth wall plate being the clock leader, it is now just the boundary clock between version 1 and version 2. So it's receiving the clock from PTP version 2, and then it's retransmitting out a PTP version 1 domain to other devices on the network. So that device is our boundary clock between version 1 and version 2. Okay. Scenario 7. So here's what we're going to do. We're going to introduce Dante to our DSP design. And what that's going to do is now let our DSP speak both PTP version 2 and PTP version 1. And because that fact, the core can now become, based on priority values that are set by default, the core can now become a boundary clock between version 1 and version 2. So in this particular scenario, what's going to end up occurring if we use our priorities out of the box, our Bluetooth wall plate is going to become the clock leader for the entire segment, and the core is going to be our boundary clock between version 1 and version 2. So that Bluetooth wall plate had the lowest MAC address of all of the devices that have that can be a clock leader. Okay, so that's why that wall plate was selected. Okay, now one more scenario. What we're going to do is set our priorities lower and have our core win the election and be both the clock leader for version 1 and version 2 and be the boundary clock between version 1 and version 2. So it's going to transmit out a pulse, a clock pulse for version 1 and version 2. Okay? So let's actually, and one more thing to mention is when we're talking about QSys cores specifically, cores that are going to employ Dante have to stay in domain of 0, because by default all Dante devices are in domain of 0. So we can't modify that without utilizing something like DDM, Dante Domain Manager. Okay, so that's one thing to keep in mind. And one more reminder that when you have devices on the network and you have Dante controller open, and you see that preferred clock leader selection in Dante controller, what that is doing is it's taking that default value, especially if the device is AES67 capable, it's taking that value and lowering it by 1. So that's exactly what you're doing when you select the preferred clock leader in Dante controller, just FYI. Okay. So let's actually look at some real world scenarios, probably stuff that you have actually seen in your environment. Okay. So let's take this out of the box. We just plug everything into the network. We have a DSP design running, and based on our factors in play, our ceiling microphone ends up becoming the clock leader for this small meeting room, just because we did not set any priorities for the system. Now, based on a couple of different things, there could be some reasons that you might not want a ceiling mic to be the clock leader in your system. Well, what if we have what if that microphone has a cabling issue? Well, what we're going to end up what's going to end up occurring there? We're going to actually see those clocking errors occur, and then we're going to hear the audio muting in the system. Okay, has anyone experienced that? I'm sure you have at least once before. If you're getting that random muting of the Dante audio in a system, that is almost always related to clocking and or multicast management on the network. Because what we're seeing is that a clock leader is dropping off as the best clock leader on the network segment. Okay, so in this scenario, you might not want that microphone to be the clock leader. However, it's going to work, it's going to operate, and there's not necessarily anything wrong with it as long as everything else is good and in place, right? So in a small meeting room, this might not be a problem. But now let's consider this. What if we have this, this very large network, and all of these systems are the same. They have a microphone, they have cores, they have peripherals, they have all this other stuff, and all of these systems are going to clock together. Well, what's going to occur if let's say we have one of these systems is a portable system, so it's something that we would roll into a classroom. It's something that we that's not always plugged in. Well, what ends up occurring out of all the devices in this massive network here, this ceiling mic ends up being our clock leader. Well, what happens if after the event, and keep in mind there may be other classes going on in these other rooms or meetings going on in these other rooms, and someone goes and unplugs that portable system? Well, guess what's going to occur? The BCMA is going to run, and we're going to mute all the audio for all of those systems until a new clock leader is determined. Okay, so that is an example where we do not want the microphone that may not always be there. We don't want that to be our preferred leader. So in QSys, one of the things that we might want to do is set a priority so that a core or a system, a DSP that's always online, that's always generating that clock, we might want that to be our clock leader so that we avoid those muting events. Okay, let's take another much larger scenario. What if you had a whole airport paging system, right? So there's hundreds of speakers, there's hundreds of microphones and hundreds of amplifier channels, right? So very massive system. So depending on a number of factors, especially in QSYS, you're going to have a core that's going to become our clock leader between the two redundant cores. But let's say we left all of our priorities the exact same, and then a year into it, the gift shop or one of our convenience shops says, "Hey, I want Bluetooth, and I want a Bluetooth wall plate, and I want that to go across the speakers in my area." Right? So someone comes in and they plug in these Bluetooth wall plates. Well, guess what's going to occur on that network because our priorities are set to default, and this device is capable of AES-67. Guess what's going to occur? The BCMA is going to run, everything's going to mute, and now a Bluetooth wall plate is now going to provide the network clock for our massive paging system in our entire airport. Now, you can probably think about why that might not be a great scenario, right? It'd be possible for this device to, one, go down, for it to be unplugged, or maybe the network cable gets cut, something like that. Now our entire paging system is going to mute until a new clock leader is selected. What we would probably want to do in that scenario is set a lower priority for our design so that the core ends up being our clock leader. And this is one of the final things that I'll point out, is that if we have a very large deployment between a bunch of classrooms and maybe an auditorium, and then we have a device that is plugged in for events and only for events, but it also has the lowest MAC address of all the devices on the network. If we come in and we plug that device in for all these classrooms, the auditorium, the PA system, that device is going to end up becoming my clock leader. And again, we can see why that would not be the preferred scenario. We would want to set one of our cores or DSPs to be our preferred clock leader in this scenario. Okay, so QSYS, in this particular case, QSYS would allow us to set alternate domains for these other classrooms and the PA system, because we're not utilizing Dante on any of those other cores. But for instance, the auditorium is going to be utilizing that remote input that's going to be plugged in and taken away before and after events. And so in this scenario, we can set our auditorium core to always be our network clock for that domain of 0 when we're utilizing Dante and AES-67 or QLAN. Okay. So one of the big takeaways here is that PTP version 1 is Dante, PTP version 2 is QLAN and AES-67. These two things are not compatible with each other, so there will always have to be a boundary clock device selected in our infrastructure, our PTP infrastructure. It is always ideal that the same device is both our PTP version 1 and version 2 clock. So that device will be the boundary clock between version 1 and version 2. And we can influence that by setting our priority values, especially in QSYS DSPs. Or in other scenarios, we can set preferred master in Dante controller to decide who or what is our preferred leader on the network. Okay, so I had to rush kind of near the end there, and I know there's plenty to go over, maybe plenty of questions, but I wanted to give time for us to ask any questions based on the content that we've covered. Has anyone found it useful? Does this anything spark any thoughts, any gears turning, anything like that? So I see there's a few things in the chat. I was not picking out the chat. Let's see. It looks okay.
I think we're up to date on questions.
Okay, yep, so, yep.
If you look at Bill's.
Yeah, okay. So what is AVB? So AVB is one of the other audio standards out there in the world, out there in the industry. Some manufacturers use that. So DNB, L Acoustics, Biamp, and a few others in the industry utilize AVB for their primary transport from device to another device. AVB comes with its own set of nuance. So one thing to keep in mind is that in a typical AVB network, the network switch is actually going to provide the network clock, and that's typically utilized. That's typically utilizing general PTP, which is different from version 1 and version 2 that we discussed today. When I connect an encoder and client on different VLANs using a PUIM router, does a clock election happen before the stream is established? So, a PIM router. Good question. So PIM is a push protocol, right? So instead of subscribing, we're going to push that to a rendezvous point, and then we're going to send it to devices that need it. So not knowing exactly what device you're talking about, if we're sending clocked audio between VLANs, now one thing to keep in mind is that Dante, out of the box, as it stands, no Dante Domain Manager. It is a layer 2 protocol only, which means that it is not designed to be routed through a virtual switched interface or an SVI. So, but you typically are not going to be sending Dante between VLANs unless you're doing something just like a VLAN translation between two network switches or infrastructure. So a multicast media stream. So so the clock election. So there's two different things that we're talking about here. So you have the clock, the network clock, and then you have the audio. So in that case, if you are sending that audio from one VLAN to another VLAN, there has to be a PTP clock established between those two VLANs, between those two devices. And so if that connection, that would have to be established first for us to get audio from one place to another. So by default, if you're sending that to another device, the BCMA is going to run, and before that clock is established between the two devices, you're going to mute the audio. Does that help answer that question, Davis? Okay. Any other questions? Happy to, if you send them to Jim or send them to me, either way, I'm happy to answer those. And keep in mind, everyone, there's plenty that we didn't cover today. There's so much to talk about, but hopefully we found some usefulness in talking with Dante and AES67 devices. So another minute left. So any other questions? All right.
Well, I'll ask one.
Okay.
We talked about domain 0 being what you see as, of course, the default for many devices and what's in most systems. Do you advise people to start with a different domain just in case other people plug in things without knowing their conventions and naming schemes, and to keep other people from unknowing, stepping on their shoelaces?
So that's a really great question. One thing to keep in mind that if we're talking about Dante, and it is a device out of the box, no Dante Domain Manager in play, by default, you will always be in domain 0. So if you plug in another device, and by chance, if that other device has a lower MAC address, you're going to get that muting of audio until the BCMA runs and a new clock leader is selected. And if it has a lower MAC address, that device is going to become the clock leader. Grant had a question. Anything you want to mention with PTP version 2 aware switches or any managed switches that don't play well with? That's a loaded question, Grant, but I'll say this really fast. So loaded question. So there are a lot of PTP enabled switches out there, and a lot of devices out there can utilize a transparent clock between ports on a switch. So one of those manufacturers that a lot of the AV industry resells is Netgear. Netgear does support transparent clocking. However, very often we tend to see issues when utilizing that feature unless it is enterprise grade equipment. So an example of that would be like Extreme or a Cisco Catalyst series, like the 9000 series. Those are going to be capable of actually providing transparent clock. Otherwise, other switches without a lot of care taken could potentially introduce PTP issues. So loaded question, great question, but loaded and plenty of nuance there.
Awesome. Any final thoughts from anyone? Additional questions we didn't quite get to?
Any questions?
All right. Well,
Great.
thank you, sir, very, very much for your time. Great content. I appreciate you setting the stage and talking about some other flavors and, everything that you presented. It's a lot to think about, and hopefully folks learned quite a bit from being here. So
happy to do it. Thanks, everyone. Have a great rest of your day. Thanks.
take care. I'll see you on the next call.